Welcome back. So in this video, we're going to be looking at the second classes of power plant engineering. In our previous video, we studied about steam turbine power plant. Now in this video, we are going to be looking at is gas turbine power plant. So what are gas turbine power plants? A gas turbine power plant is an internal combustion engine that is used in converting chemical energy gotten from fuel to electrical energy. So an internal combustion engine that is used in converting chemical energy gotten from fuel. The fuel can be any fuel, it can be a natural, it can be gotten from hydrocarbons, it can be gotten from they have different classes of fuel. So any class of fuel, right, it converts it to electrical energy. That is a gas turbine power plant. Now, the purpose or one of the advantages of a gas turbine power plant is that despite its size, it's still able to produce a high amount of power. So that is one of the advantages of why gas turbine power plant is mostly used in in some industries. Now we use it in civil aircraft, we use it in military aircraft, and the other applications, other areas where a gas turbine they are used. So now that we've established the meaning of a gas turbine power plant, let's now look into the categories. So under gas turbine power plant, we have the ideal gas turbine and we have the real gas turbine. Both the ideal and the real gas turbine, they operate on a Brayton cycle. So an ideal gas turbine, for the sake of this course, we'll be using GT. So an ideal, the sake of this course, we'll be using just GT. An ideal gas turbine, it operates on a Brayton cycle. You can say an ideal Brayton cycle. Whereas for a real gas turbine power plant, it operates on a real Brayton cycle. Now these two, they are also called Joule cycle. I call it Joule cycle. So now we've known the meaning of gas turbine power plant and the two categories. So in this course, we're going to be looking at these two systems. So we'll look at the ideal first, then go to the real gas turbine power plant. So for the ideal, starting with the ideal gas turbine power plant, we have both an open system or a open cycle and a closed cycle under this ideal gas turbine power plant. So for the open cycle, let me call it A. For an open cycle, let me show you how it looks like. Now, let me reiterate, before we've already established the meaning of a gas turbine power plant, you should also know that a gas turbine power plant has three major components. What are the components? It has a compressor, a turbine, and a combustor. So that's what I'm going to do now. So for an open cycle, it looks like this. You have a compressor, this is a compressor, then you have this thing, I'm going to use CC to indicate. This CC stands for combustion chamber. So you have a compressor, is entering this compressor at 1, then at 2 enters my combustion chamber, comes out and goes to my turbine. So this is my turbine. So now picture this. This line that you are seeing I'm drawing is, imagine it as a pipe. So the fluid entering this compressor, most times for the gas turbine power plant, the working fluid is mostly air or gases. The fluid entering this compressor, what the compressor does is to reduce the volume. So what the compressor does is that it reduces the volume of the air, shrinks it, and in the process of shrinking it, what happens? The pressure and temperature increases. That's what comes out here. So at my point 1, the volume is large. See the diagram. From the diagram, you can tell that the volume of air is large, but once it's coming out at a smaller volume, but the pressure and temperature increases at point 2. Then it enters our combustion chamber, and in the combustion chamber fuel is being added. But because this is an ideal gas turbine system, we usually assume that the fuel is not added here. We'll look at all those fuel and analysis in our real gas turbine, but for this ideal, we pretend that fuel is not added here. But let me explain what it means. So Already this point 2 is at high pressure and temperature. In our combustion chamber, fuel is being added, and for combustion to take place, you need three things. Fuel, you need oxygen, which is this air that's coming, and you need an igniter, which is heat. So mainly these three things come together, combustion takes place. That is what happens in the combustion chamber. The what is coming out in point 3 is the combustion product, the flue gases. We call it flue gases. That's what's coming out at point 3. The product of the combustion at point 3. Then, because immediately combustion takes place, it has heated that working fluid air to a very high temperature. Already the temperature is high here, but because it's inside the combustion chamber and combustion is taking place, what's coming out here is an even higher temperature compared to this one. So that is what will rotate this shaft in our turbine. So this is called the shaft. So because of this high pressure and temperature of this point 3, it will rotate my turbine, generating electricity. Then the exhaust gases is what comes out as for the waste. So this is called the exhaust gases. So these are the waste coming from this process. Now the waste for an open cycle, the waste is being released to the atmosphere. So this is for an open cycle under our ideal gas turbine. This is what it looks like. These three components. This is a compressor, this is a combustion chamber, or we call it a combustor, and this is a turbine, and this is our shaft. So we have about in this case we have like three processes. So let me just put that down. Process 1 to 2 is called isentropic, it's called an isotropic compression. So what happens in this our point 1 to point 2 or state 1 to state 2 is an isentropic compression. Isentropic means that we are pretending, since we are under ideal gas law or ideal gas turbine, we are pretending that there are no losses. But in reality, there is always loss happening in our compressor. It can be friction loss, heat losses, etc. This irreversibility or losses makes it not to be an isentropic process. But because we are dealing with an ideal gas turbine, we pretend that it is isentropic. So that's for process 1 to 2. Then for process 2 to 3, we call it constant pressure, or you can call it isobaric. Call it isobaric heat addition. So like I said before, that in this combustion chamber, heat is actually added. So process 2 to 3, we have isobaric heat addition. Then from process 3 to 1, which is our last process, we call it isentropic expansion. So if you look at process 3 to 1, same thing with compressor. We are assuming that there are no losses applies here to that assumption because we're under ideal process. So this is an open cycle for an ideal gas turbine. These are the components for an open cycle for an ideal gas turbine. Okay, so let's go to the second one. If it's a closed cycle, let's look at if we are dealing with a closed cycle. Now, if it's a closed cycle, what happens? The closed cycle, we replace this combustion chamber with a high temperature heat exchanger. Then, this exhaust gas that we are allowing to be released to the atmosphere, we are going to cool it down using a low temperature heat exchanger. So there are two things involved. For a closed cycle now, remember, look at the shape of this. From the block diagram, you can see it's clearly open. But in a closed cycle now, all the components are connected end to end. There's no open space. So we replace this combustion chamber with what? A high temperature heat exchanger, and replace this exhaust or put a component, this exhaust gas with a low temperature heat exchanger. So we have this. Our compressor still remains the same. So this is our compressor. You already know. Coming out, we have point 1 entering. Instead of me to have our combustion chamber, I have this. This is our high temperature heat exchanger. Heat is being added, so we call it QH. Heat is being added, so that's why there's an arrow going in. Then you have our turbine. So what's coming out here is going here. Instead of it to go to the atmosphere, we channel it back using another heat exchanger. But this is called a low temperature heat exchanger. So in this one, heat is being rejected. So we have Q L. That's what we use to denote it. Let me check if we have written all the states. So what is entering this compressor is at state 1. It's coming out at state 2. Enters my high temperature heat exchanger, comes out at state 3. Then goes to my turbine, comes out at state 4. Then comes out here at state 1. So this is a closed cycle. So this is a closed cycle, how it looks like. Now, in this closed cycle, same thing applies here. The same way we are updating processes, we also have processes for a closed cycle. So it's exactly what you have here, but now in this one we have included process 4 to 1. So I will just add it here. Every other thing repeats in this place. So I'll just include it here. We have also process 4 to 1. And what is process 4 to 1? It is isobaric heat rejection. Heat rejection. Okay, now with this knowledge, we can now draw our TS diagram. So let's draw our TS diagram. The reason why there's no TS diagram for an open cycle is because TS diagram, it is simply a cyclic process. In this place, is not exactly cyclic because of there's an open space. So this one is matches something we can present using our TS diagram or PV diagram. But in this course, I'll just be making use of TS mostly. So let's look at the TS diagram. So this is my TS diagram. Process 1 to 2, we've already listed, we said here is isentropic compression. So since it's TS, and this is the entropy line, I'm going to draw a straight line to show that it is what? Isentropic. So from my point 1 to my point 2 is a straight line. Let me shorten this a little. So this is process 1 to 2 is isentropic. This is simply saying that why we call it isentropic because S1 is equal to S2 as it's a straight line. Then our next process is what? Isobaric heat addition. So I'll come here. In the process of adding heat, what happens to the temperature? Temperature increases. So from this point, I will show there's an increase. And in the process of adding heat, right? Also the entropy increases. So both entropy and temperature are increasing. So to represent it, we did like this. This is saying that the temperature is increasing, as you can see, and the entropy is increasing. So that is my process 2 to 3. Then finally, what? Our process 4 to 1. They said it's isobaric. Sorry, 3 to 1 is isentropic expansion. So another straight line. So 3, but here it's supposed to be 3 to 4. Sorry, 3 to 4. That's what is happening here. In this case, we didn't have. Sorry, I'm supposed to put 4. So this is 3 to 4. A straight line. This simply means what? That S3 is same thing with S4 isentropy. Then finally, we have 4 to 1, which is isobaric heat rejection. So it comes from here and goes back. Just that way. This is my 4 and quick correction. So this is my TS diagram. Now, in this TS diagram, there's something you observe. If we trace it to the temperature line, let's see what we have. At this place, we have T1. At this place, we have what? T2. If we trace again, you can see that T4 is slightly above T2. Then the highest temperature we have is called T3. So a side note is that you should know, what you should know is that T3 is always the maximum temperature. So T3 stands for our maximum temperature. Then T1 is our minimum temperature. So anytime they are referring to maximum temperature, what should come to your mind is T3 and maximum temperature is T1. So with that said, now we are still under ideal gas turbine power plant, right? So let's now do some thermodynamic analysis based on what we have done. Let's quickly do a little analysis to get our thermal efficiency. The first formula we will do an analysis for is the thermal efficiency. So the thermal efficiency, we usually represent it with this, and mathematically we know it is the net power divided by QH. What is this net power? The net power is simply the power that is produced by the turbine minus the power that is consumed by the compressor. So this is the power produced by the turbine minus the power consumed by my compressor divided by, now this QH has a lot of names. You can call it the heat input rate, right? Or you can call it the heat addition rate. So this is QH and it's gotten from this place, QH dots. Now under this thermal efficiency, let's do the analysis. Let's take them one after the other. You can start with the compressor. Power absorbed by the compressor. Or we can simply say the compressor power. Let's look at the compressor power, which is WC. So mathematically, the formula for compressor power from first law of thermodynamics, when you do the analysis, you take assumptions, right? What you're going to have is simply the mass flow rate times. Now, my compressor is in between which two states, point 2 and point 1. So it's simply mass flow rate times H2 minus H1. If I don't want to write this in terms of enthalpy, I can still go further and write it like this, because we know that enthalpy is equal to Cp dt. So if I want to change this enthalpy to temperature, I can simply write it as this: mass flow rate Cp T2 minus T1, because of this relationship. So now that we've done that, let's look at something together. Now, write up, we can still go further to simplify it if we want, but I don't think that is necessary. But in our compressor, remember we said that we are still under an ideal gas turbine power plant. So in an ideal gas turbine power plant, we are saying that in this compressor, it is isentropic, there are no losses. So anytime you're dealing with an isentropic process, there's a relationship. So an isentropic process, for every isentropic process in this compressor now, from process 1 to 2, it is simply T2 over T1 is equal to P2 over P1, everything raised to the power of gamma minus 1 over gamma. That is the isentropic process. For something to be isentropic, that there are no losses, it is what? This relationship. Temperature at the outlet, compressor exit or outlet, divided by T1 equals to P2 over P1. Now this P2 over P1 stands for the pressure ratio. So I can still go further and write this as T2 over T1 is equals to ROP, pressure ratio. Now this gamma is the ratio between the specific capacity at constant pressure to the specific capacity at constant volume, Cp over Cv. So if I make T2 subject of formula, what I will have will be what? T1 times ROP gamma minus 1 over gamma. So anytime in the question, most of the times they will not give you T2. You will only be given T1. So if you are given T1, you can use this relationship for an isentropic process 1 to 2, and get T2. So substitute it there, then you will not be able to get your compressor power. So that is for compressor power. Now, if they now say if you don't calculate compressor power, you calculate the compressor work. The compressor work is denoted as small wc. Now, it is simply equal to this power of the compressor divided by mass flow rate. That's all. So from this formula that we have from our compressor power, if I divide it by mass flow rate, that is my compressor work, and it is equal to H2 minus H1. That is it. So if a question asks you to find the compressor work, you just have to divide the power by the mass flow rate and you get the compressor work. So we have understood our power in the compressor. Let's go to the power in the turbine. So for the turbine power, I think we should use the other side of the board. That's number 3 now. We are going to turbine power. Now for the turbine power, what are we going to do? The turbine power is simply W dot T, and same thing we did here. It is the mass flow rate. I've cleaned the part of the board, but you saw that our turbine was in between 0.3 and 0.4. So it is just H3 minus H4. And if we don't want to use enthalpy, we can write it in terms of temperature. So it is going to be what? Mass flow rate Cp T3 minus what? T4. Just like what we did here. Again, since we said that it is an isentropic process, we can apply that relationship. So for an isentropic process in process 3 to 4, right? What do you see? You say it's going to be what? Now it will be T3 over T4 is equals to P3 over P4. Everything raised to power gamma minus 1 over gamma. Now, let's assume that I'm looking for T4 because in our questions, most of the times, you'll be seeing two types of temperature, minimum and maximum only. If you are given minimum temperature, what you will do is with the minimum temperature you can get You can get your T2 using this relationship. While if it's in the maximum temperature T3, you can get your T4. Let me show you. So if we invert both sides, we already know that P3 over P4. Hold on. P3, P3 over T4. Then P3 over P4 is pressure ratio. If I want to invert both sides so I can get T4, I will have this. T4 over T3 is going to be equal to what? RP, then the sign will change it to be 1 minus gamma over gamma. That's what you have. So with this now, I can comfortably get my T4. So my T4 is equal to T3 pressure ratio 1 minus gamma over gamma. So this is my T4 formula. So I'm saying that if the question gives you maximum temperature, what you just need to do is to use this relationship and get your T4. Okay, so we've gotten turbine power. Let's get our turbine work. In case question asks you to get turbine work. It's still similar with what you did here. Turbine work is small Wt and it is simply the turbine power divided by the mass flow rate, and it will be equal to what? Cp T3 minus T4. So this is the formula. So these are the formulas that we need. So we've gotten this, we've gotten it. Let's get this QH. So this QH, remember we said we call it, you can call it the heat input rate, QH. And QH, check your diagram, the block diagram we drew for a closed cycle. You've seen that our QH, that place that is being added, is in between point 3 and point 2. So what we just need to do is to use it here. So it is mass flow rate, H3 minus H2. Then in enthalpy, sorry, in temperature is going to be what? T3 minus T. So this is everything we need to know now, thermal efficiency. So that's the analysis for thermal efficiency. And the second formula that we need to remember is called the maximum work ratio, maximum possible pressure ratio. It's called the maximum possible pressure ratio. So maximum possible pressure ratio is denoted as RP max is equal to T3 over T2, everything raised to power gamma over gamma minus 1. Then the last formula is called the optimum pressure ratio. The optimum pressure ratio. So what's the optimum pressure ratio? It is simply equal to T3 over T2, everything raised to power of gamma over 2 brackets gamma minus 1. So this is the optimal pressure ratio. So for this level, I think we should just stick with these formulas we use to solve any problem that we can find. Okay. Now, the same way, remember that this ideal gas turbine power plant, it is simply a heat exchange, a heat engine. It is simply a heat engine. Now, because it's a heat engine, every heat engine can obey or can operate rather on Carnot cycle. So if the question asks you to calculate this gas turbine power plant when it's operating on Carnot cycle, what you're going to do is this. So let me quickly. So when our ideal gas turbine is operating on a Carnot cycle, what happens when it's operating on a Carnot cycle? So what we are going to do is simple. A Carnot cycle operates between two temperature reservoirs. So you have something like this. If I want to illustrate it, you have this, you have this, and you have this. Now, this is our heat engine, which is representing our ideal gas turbine, right? Now, this is where we keep our temperature, our high temperature. This is where we keep our low temperature. In this our ideal gas turbine power plant, I just told you that we have maximum temperature and minimum temperature. So the maximum temperature we said is which temperature? If you can remember, we said it is T3. While for the minimum temperature we said it is T1. So here our T3 serves as our TH, while our T1 serves as our TL. So anywhere you see T3, I can use TH to represent. So anywhere you see TH, I'm referring to T3. Anywhere you see T1, I'm referring to. And since it's a cyclic process, right? This is a heat engine, and heat engines, they are cyclic and work producing. So the arrow is going this way, and the work will be coming out like this, our compressor, because it is a work producing engine. So it's producing work. At this place, heat is being added from this or removed from this reservoir as Q dot H to this heat engine. Then we remove or reject heat from this our heat engine as QL. So QH refers to the heat that is being added to our heat engine. The heat engine heat, while QL is the heat that is being rejected from our heat engine, QL. So anytime we have a Carnot cycle like this, it's simply saying that it's obeying our first law of thermodynamics, meaning that this our W net that we talked about is equal to Q net when our gas turbine is operating on Carnot cycle. The W net is same thing as Q net. So if I want to get the efficiency here, the efficiency is simply, remember initially our efficiency is W net over what? Q dot H, abi? Good. Now that I've said this, for every Carnot cycle, for every heat engine, there will be a first law. This W net will be equal to Q net. So I can replace this W net with this. So now be Q net over what? QH. And this Q net, if you break it down, you know that it's QH minus QL divided by QH. So if I simplify further, I will have what? 1 minus QL over QH. So this is what you have from a Carnot cycle. And also, if you still want to go further again, you should know that QL over QH is similar with TL over TH. So my formula can be simplified further to this. 1 minus, instead of me putting this, I'll put of TL over TH. So whenever my gas turbine power plant is operating on a Carnot cycle, this is the formula that we are going to make use of. So I hope you've taken note of that. So this is everything you should know on an ideal gas turbine power plant. So we'll be going into the real gas turbine power plant. I think gas turbine power plant is quite simple because we pretend that there are no losses. But for a real gas turbine power plant, we are going to be considering those losses. So while we are back to the real gas turbine power plant. Now for us to study this real gas turbine power plant, I've already explained that for a real gas turbine power plant, we are going to consider the losses. Those isentropic processes are not actually isentropic in reality. They are presence of pressure losses, friction losses, and other heat losses. So what do? Let's consider it here in full. So what I'm going to do first is to draw the TS diagram for our ideal gas turbine power plant. What it looks like. You already know how it looks like. It looks like this. This is our TS. Put our T and our S. Then you have this process 1 to process 2. Then have this going to process 3, then comes down a bit as our process 4, then meet here. So this is what we have. This is for an ideal gas turbine. But what we are going to be looking at is real gas turbine power plant. So we're going to be making some amendments to this diagram. What's the amendment? Now, process 1 is isentropic. On the word isentropic means that it's supposed to be straight. S1 and S2 are equal, but reality is not so. So the real diagram should be this. So this is what it should look like. Let me draw this properly. So this is our, let me make the amendment now. I have something like this. So this is 2A. This is simply telling us that this is the real or actual system. So this diagram is the real one. This is the ideal. Now, same thing applies here in process 3 to 4. In reality, there is not a straight line. There is a deviation, a curve. So let me quickly do that. So we have 4A. And I forgot to also include the constant pressure. So at this place, we have constant pressure line. P2 and the pressure here are the same. P2 equals to P3. Same thing here, and the pressure here are the same. P1 is equals to P4. So let's look at it together. Now, as I've said before, if someone is to ask you what are the temperatures or what are the points or state of this real gas turbine power plant, it is simply 1 to 2A, then 3 to 4A, and the process continues. This 1 and 2 is not included in the real gas turbine. This is ideal side. Same thing with 3 and 4 is not for an ideal. It's not for the real. This is for an ideal distance. So the real gas turbine power plant is actually this point 1 to 2A, then it goes to 3, then it comes back to 4A, and it goes back. So this is how it looks like. Now, at this place, remember we said that they said before they are isentropic, right? The reason why the isentropic is there for ideal is because we consider it to be 100%. But in reality, the isentropic efficiency is not 100%. When it was ideal, the isentropic efficiency is 100. In this case, it is not. So in cases where you'll be given isentropic efficiency of 80, 90, anything below 100, the formula for isentropic efficiency, we represent isentropic efficiency using this. Isentropic efficiency of, let's start with this one, the compressor. So isentropic efficiency of our compressor, let me do it this way, C comma I is equal to what? Now we have two work that is done here. We have this work W2 minus this place minus this place, right? I have another work too minus 1 down here. So I'll ask you now, if you look at the length of this and this, which one is bigger? In our isotopic efficiency, we are trying to make it a proper fraction. A proper fraction means that the numerator should be smaller than the denominator. The denominator should be big enough to carry the numerator. That's what proper fraction is. So I want the smaller size of this spacing to be at the numerator, while the bigger one will be at the denominator. So if you look closely, what are you going to have? See this, from 2 to 1, it is a smaller size compared to this. And you know that this smaller size is what? Is it actual work or ideal work? From 2 to 1 is the ideal, then 2A to 1 is the actual. So the smaller one will come up first, which is the actual work, divided by the what? Ideal. Sorry, the ideal work, because this is the ideal one. Sometimes they even put a 2I to tell you that this is 1 to 2I. This is the ideal. So this is the ideal coming up, followed by the actual. So that is for our compressor. Now let's do the same thing for a turbine. So look at your turbine. Let's find the isotopic efficiency for our turbine. Remember, if it's 100%, it should be a straight line. But once you are given an isotopic efficiency that is 100%, whatever the number may be, you have this curve. And this curve from point 3 to point 4 is the actual, while from 3 to 4 itself is the ideal. So this one, what is it going to look like? We are going to start with the smaller one over the bigger one, and we can clearly see that this is small compared to this length. So we are picking this one first. And this is the actual or ideal. This is the actual. So we have the what? Actual work over the what? Ideal work. So this is how you're going to represent it. Now, if we want to break this thing down and write the formulas, it is simply what? This is I want to write it in terms of this work. We can write it in terms of temperature instead of enthalpy. So I want to write this ideal work. Ideal work is WCI. Actual work is WCA. Same thing applies here. So if I want to write this work in terms of temperature, I'm going to have T. Remember we are starting with ideal. So it's going to go T2I minus T1 divided by, then the answer follows, T2A minus T1. So in most cases, you'll be able to find T2A. So let's just at once make T2A a subject of formula for me. If I make T2A a subject of formula for me, what am I going to get? I'm going to have T2A is equal to T1 plus T2I minus T1 divided by the isentropic efficiency at the compressor. This. So this is what most times you'll be asked to calculate T2E. Now that aside, let's go to this one, the one for the turbine. So what are we going to do for the turbine? So for the turbine, the same thing we are going to do. This is the actual WTA, why this is the ideal WTI. So if I write the formula out, what am I going to get? At the actual, I have here T3 minus T4A divided by, now this one to be use I to represent it to show that it's ideal. So divided by T3 minus T4I. So if I make, remember the same thing we did here, the point of interest is always this T4A. Let's make T4A subject of formula. If you do that, you're going to have T3 minus efficiency times T3 minus T4I. So this is what you're going to have as your T4A. Now this, all this we're doing is simply just for real how a real gas turbine really operates. Right? So remember something I showed you at the beginning, that in that combustion chamber, right, fuel is always added and oxygen or air coming from the compressor exit is added. So in the process of adding fuel and oxygen or air, what happens? Then we ignite. You see combustion takes place. But when we consider ideal gas turbine, the we're not considering the fuel. But in this case, we're going to be considering the fuel. So let's quickly just do that. Let me show you how it looks. So let me show you how it looks. Now we have this. Let's see if we can still remember. Before we go into that, let's talk about the combustion efficiency. Combustion efficiency is denoted as this. And mathematically, combustion efficiency is always T3 prime minus T2 divided by T3 minus T2. Or sometimes it can be mass flow rate of fuel prime divided by mass flow rate of fuel. I believe if you are asked to calculate this combustion temperature, you'll be given this value. Then you have to just do this calculation and get it, or you'll be giving this and this. But most of the times, you will be given the combustion efficiency already. No need to calculate it. Okay, so now this is for combustion efficiency. Let's look at a relationship. There's a relationship between the heat coming from the fuel and the combustion temperature rise. So the heat from fuel, I will explain the heat from fuel, relationship between the heat from fuel and the combustion temperature rise. So the heat from fuel is always denoted as Q dot F. This is what will come from fuel. The value is always equal to the combustion temperature rise is the same thing as Q dot H. So bear in mind, so Q dot H, and I've showed you that Q dot H is the heat input that we talked about in between point 3 and point 2. Now, if you want to rewrite this in full, the formula for this heat gotten from fuel is simply the mass flow rate of fuel times HF. This is mass flow rate of fuel. This HF is the calorific value of the fuel. This is for the fuel side. Then this is for the combustion temperature, right? You remember the formula we wrote? It is that mass flow rate multiplied by Cp times T3 minus T2A. Now, why are we picking A? In this particular real gas turbine power plant, our combustion is taking place in between 3 and 2A, not 2I. Remember that for our real gas turbine power plant, the cycle is actually 1 to 2A to 3, 4A, and back to 1, not 2 or 4I. So that's why the combustion is taking place in between just 3 and 2A. Okay, so this is a very, very important relationship that we usually use. And most of the time, sometimes we're used to use it to calculate T3. So with this, you just have to make it a subject of formula from here. So let's go back to what I said. Now, from that, this is just some side note you should take note of. Some things you should take note of. Now, let's go to our combustion chamber. In our combustion chamber, you have something like this. If you remember, CC, then you have a line coming from here and a line going out. Now, at this point, we have, this is point 2. At this point, this is point 3. If you check your note, you see what we just did recently. Now, at this point 2, heat is coming into this combustion chamber. And remember that I told you now that for real, we'll be considering the fuel. So we have fuel coming from here. So here is our air, here is our what? Our fuel. And when these two collide, what happens? Combustion takes place, the presence of heat. So this place that is coming here is called our flue gas. Call it flue gas. These are the combustion products, point 3. So here I can write the heat coming out. Mathematically, the heat coming out from air. It is what? M mass flow rate of air, Cp of air, and T2. While for fuel, it is what? Mass flow rate of the fuel and calorific value of the fuel. And finally, for the flue gas, I will have mass flow rate of my flue gas, Cp of the gas, and T3. Now, if we perform energy balance, what's energy balance? What is entering equals to what is leaving. So what are entering? And this one are entering this. What's leaving this? So let's add the entering. So using energy balance, it is energy going in equals to energy going out. So let's look at it closely for the one that is energy going in. The energy going in is this one, which is what? Mass flow rate of air, Cp of air, T2 going in. Which other one is going in? This one. Plus mass rate of fuel, HF of fuel is equal to energy going out is what? This one. Mass rate of the gas, Cp of the gas, T3. So just bear in mind that all these are another ways to get T3. You can either use this process, get your T3, or use this one. Although both of them will give different answer, but this particular one is the more accurate way of getting our T3 if you have to find T3. So you don't make T3 subject of formula here. And if all these parameters are given, you substitute to get your T3. So that will be all for this particular class. So in this class, we looked at our gas turbine power plant, the meaning of gas turbine power plant, their categories, we looked at both ideal and we looked at the real gas turbine power plant and their formulas. So in our next video, we'll be looking into the modifications of gas turbine power plant. Please, if this video has helped you, kindly like and subscribe and share with your friends. Thank you and see you in our next video.